Section 5.1 Polynomial Functions. When we look at polynomial functions, a certain type of a function, we can actually find out a lot about it just from looking at some of the x's in the algebraic symbols. So polynomial functions, we've already looked at linear functions. Linear functions are a number times x plus a number. And we've also looked at quadratic functions where there's some sort of x squared term. So if there's an x squared term, that's the biggest, that's a quadratic. If there's just an x, that's a linear. Both of linear and quadratic are examples of polynomial functions. What a polynomial function is technically is a polynomial function on one variable is a function of the form where we have the function is equal, the set of directions are, this means a number, whatever number that happens to be, times x to a power, plus another number times x to a smaller power, plus, and we could keep on going and going and going until we run out of powers for the x. So a number times x plus another number. All these numbers that are in front are called constants. They're all the numbers in front. They could be whole numbers, decimal numbers, fractions. They're the number in front of the x's, and they're called coefficients of the polynomial. N is greater than or equal to 0 is an integer, so all the powers have to be numbers that you could count up to on your fingers, so or using toes, but these powers all have to be numbers that you can count up to, so they're whole positive numbers, and x is the variable. If a sub n, meaning if this right here does not equal 0, it's called the leading coefficient. If this was 0, this term wouldn't be here, so then the next term would be the leading term. So here we have leading term, the number in front is leading coefficient. Leading term, leading coefficient. And n, the biggest power, is the degree of the polynomial. The domain of a polynomial function is a set of all real numbers, so we can put any number that we want into a polynomial. Some examples of a polynomial function. If we have the function f of x is equal to, let's say, 5x to the 9th minus 4x plus 3, that would be an example of a polynomial function. If we had the function f of x is equal to 7, believe it or not, that is a polynomial function. All the leading terms in front of the x's were zeros, and we're left with that constant, but it's still a polynomial function. If we have the function, let's say 3x squared plus 5, that's a quadratic, but it's also a polynomial function. Something that is not a polynomial function would be something like this, where f of x is equal to 3x to the minus 1. This is not a polynomial function because the power is not a positive whole number. And where this actually is coming from is 3 over x, or 3x to the minus 1 is equivalent to 3 over x to the first power. That power, or that x, is on the bottom, and so the domain would not be the set of all real numbers because we can't have zeros in the bottom. So this is an example of a function that is not a polynomial function. Another example of a function that is not a polynomial function would be something like the square root of x. Not a polynomial function. It's a function, just not a polynomial. Some additional vocabulary that goes with this. Each of the individual x terms are monomials. So each individual term is a monomial. And the leading term, if it doesn't equal 0, again, the leading term is what's out front, the term with the biggest exponent. That whole thing is the leading term. The constant is just, the leading coefficient is the number in front, and then the constant term is the last term, the term without any x's. So leading term has largest exponent, and the constant term is the term without x's. That's how that works. Some more vocabulary yet. The zero polynomial is if all coefficients of a polynomial are zero. The polynomial is a zero polynomial and has no degree. That would be like the example where I did f of x is equal to 7. All the coefficients, or all the numbers in front of the x's, are 0. The only part that's left is the constant term, and it's the zero polynomial. The degree has no degree because it has no x's. Standard form is when the polynomial is written with the non-zero term of the highest power degree. The highest power degree, we're looking for the biggest exponent first, and then continuing on down in descending order. So if our biggest exponent, we start with the biggest exponent term and just work our way down with the exponents. That's called standard form. So take a look at this one. Here we have a function, f of x is equal to 8x squared plus 13 over x plus 2. First thing off, is this a polynomial function? The answer is no. It is not a polynomial function because this x here is the same thing as 13x to the minus 1. That is not a positive exponent, a positive whole exponent. So it is not a polynomial function, which means none of those other things even make sense because those things are for polynomial functions. If we take a look at this function here, determine if this equation is a polynomial function. I see x's with powers that are whole numbers. So positive whole numbers. So is this a polynomial function? The answer is yes. It is a polynomial function. The degree is the largest exponent. So our largest exponent here is 9. It has a degree of 9. Standard form means to start with the term that has the largest exponent, which is 9, and then work down in terms of exponents. The next biggest exponent is 3, and the 182, the x value doesn't have an exponent. An exponent is 0. It's the smallest. So standard form, it was actually already written in standard form for us. The leading term is the 4x to the 9th. That's what's starting it out. The leading, I'll just add this in there, coefficient is just the number in front, so it's just the 4. And then the constant term is the term without any x's, so that's 182. Polynomials are smooth, meaning the graph contains no sharp corners or cusps. It has no spots where it's pointed. This over here, right here, this would be an example of a polynomial. It's smooth, it's wavy. This one here, we have sharp points, so not a polynomial. Continuous means that there's no gaps or holes that can be drawn without lifting your pencil. I can start tracing this one and I never have to lift up my pencil as I trace. This one here, I would have to lift up my pencil here to start over here. This one's not a polynomial. So polynomials are both smooth and continuous. A power function of degree n is a monomial function of the form ax to the n. So if there's just one term, if you only see an x in one spot to a power, that is called a power function. Just like before, a is the real number, meaning what number out front can be any number, positive, negative, fraction, decimals, and so any number we want there. And then the n is an integer, so n has to be an integer, a positive integer, greater than 0, meaning that it's something we could count on our fingers and toes. So some examples of power functions. Something like f of x is equal to 5x to the 7th, that's a power function. Something like f of x is equal to negative 19.7x to the 13th, that's a power function. Something that is not a power function would be f of x is equal to, I don't know, 3x plus 7. So this right here would not be a power function. Power functions only have one term. Some properties of power functions. Power functions, they tell us a lot about what graphs are doing. So when we look at properties of power functions, in this case we're looking at power functions where the power is an even number. So make sure when you're looking at this graph you realize that this power is even. It might be 2, 4, 6, 8, 10, 12, something that's even. F is a even function. So if you see this here is even, it means it's an even function. When it's an even function, its graph is going to be symmetric about the y-axis. So because we know it's even, we know we can flip it over the y-axis. The domain is still the set of all real numbers. This is still a polynomial, so this domain is still the set of all real numbers. The range is the set of non-negative real numbers. The graph always contains the points -1, 1, 0, 0, and 1, 1. And if you wanted to double check this point 3, all you have to do is make up your own function. We could make it f of x is equal to x to the 6. Doesn't really matter. Anytime we put, no matter what this number here is, as long as it's even, whenever we put -1 in and multiply -1 by itself an even number of times, we're going to get +1. If we put 0 in, we multiply 0, no matter how many times, we're going to get 0 out. Put in 1, no matter how many times we multiply it by itself, we're going to get 1 out. That's why it always contains those points. As the exponent n increases in magnitude, so as this exponent gets larger and larger, if we're at 200 or 400 or 600 for this exponent, the graph is steeper when we're outside of -1 or +1. So look here, as this is just x squared, well, here's a better example. So here we have x to the 8th. X to the 8th is steeper outside of that range, and it's flatter inside that range. And the reason it's steeper is because when we put something to a higher power, it's going to make it larger faster. However, in between this range from -1 to 1, from -1 to 1, when we're in between that range, it's a fraction to a power, and the more times you multiply a fraction by itself, the smaller it gets. So that's why it's flatter here, steeper here. So that's what happens there. Now this almost looks like the same thing, except in this case n is odd. So this slide, these rules are for when n is odd. If it's odd, the function is odd, so its graph is symmetric with respect to the origin. We can give it a 180-degree turn and it'll land back on itself. The domain and range are the set of all real numbers. The graph always contains the points -1, 1, -1, 0, 0, and 1, 1. Same reason as before. You can try it with a few functions if you want. As the exponent increases in magnitude, as this power gets bigger and bigger, the graph is steeper when outside of -1 or 1. So just like before, see how this graph is steeper when we're outside of there and there. The blue graph is steeper, it has a higher power, and it's flatter inside. And the same reason as before. As numbers, if any number between -1 and 1 is a fraction, well, yeah. So any number between -1 and 1, when you multiply it by itself, if you think of the examples of fractions, the more times you multiply a fraction by itself, the smaller it gets. So it's flatter here. Outside of here, once you have a number above 1, the more times you multiply a number that's greater than 1 by itself, it gets bigger faster. So that's what's happening there. More vocabulary yet. I promise there's an end to all the vocabulary. A real zero, if f is a function and r is a real number, when r is put in, if we put r in, get 0 out, then r is called a real zero of f. So if you put r in and get 0 out, it would be a real zero of f. As an example, in this example here, what would need to go in to get 0 out? So what x value would go into this to get 0 out? Well, if I solve this, I'm going to get 1 and negative 1. 1 and negative 1, those are the two real zeros of f, which also happen to be the x-intercepts for the graph. So if you find the real zeros, this is the x-intercept. And x-intercept, neither up nor down, you get out a value of 0. So same thing. Real zeros, x-intercepts are the same thing. Trying to actually take some of this information now and do something with it. So this says find a polynomial of degree 3 whose zeros are 1, 5, and negative 2. 1, 5, and negative 2. And then on the bottom I already read, could there be other polynomials that meet this criteria? So if I come up with an example, you should be thinking, is this going to be the only example? Well, if it's a polynomial of degree 3, these are the zeros. When I put in a positive 1, I should get out 0. If I put in a positive 1 here, 1 minus 1 would get 0, so that part would be 0. If I put 5 in, I get 0 out. If I put an x minus 5 here, when 5 goes in, when this 5 goes in here, 5 minus 5 would be 0, so the whole thing would be 0. If negative 2 goes in, I would need an x plus 2, so that when this negative 2 goes in here, it ends up as a 0. This right here would be a polynomial. This polynomial doesn't look quite like what we've done before, but I made this polynomial as a factored form, and this factored form, when I multiply this polynomial out, what's going to happen, eventually this x times the x times the x is going to be an x to the third. I can be sure it's going to be a degree 3. So just knowing that it's degree 3, if I think about the first times the first, there's going to be some other stuff, but then eventually that's going to have to be times by this x. It's going to be an x to the third. Just to make sure, if I multiply this part out first, we're going to get x squared minus 6x plus 5 times the x plus 2, which is going to be x to the third minus 6x squared plus 5x minus plus 2x squared minus 12x plus 10. And combining the like terms, this is x to the third minus 4x squared minus 7x plus 10 would be standard form. Now, this is a polynomial. It's degree 3. The largest exponent is 3. The zeros are 1, 5, and negative 2. I'm sure of that because it came from this right here when it was in the factored form. Could there be other polynomials that meet this criteria? Sure. What if this had been a 7 out front? If we multiplied everything by 7, would that still work? Well, yeah, because when we factor it all out, the 7 would be out front. These factors here are still going to have the same zeros. So the answer is yes. There could be other polynomials that meet this criterion. Some other things that could happen with this: if the same factor, x minus r, occurs more than once, r is called a repeated or multiple zero of f. So I'm just going to keep reading here. If x minus r to the m is a factor of a polynomial f, and x minus r to the m minus 1 is not a factor of f, then r is called a zero multiplicity m of f. Well, what exactly is that saying? So if this is a factor of this polynomial, and this is not a factor, well, if this is a factor, the only difference between this and this is the power. So this is saying if the biggest power is here, is a factor, and there's no other bigger powers, then r is called a zero multiplicity of m, meaning whatever number is right here is a zero of multiplicity this right here, however many times this is here. For example, this example right here, here, if I look at this term here, the zero that would make this term turn into 0 is 3. 3 has a multiplicity, so this term right here, there's no other ones like it. The largest exponent here is the 5. That's the largest exponent. It's a zero multiplicity. 3 is a zero multiplicity of 5. 3 is a zero multiplicity of 5. That's how many, that's what the multiplicity is. On this one here, negative 2, so it's the opposite of this. It's what would make this 0. So whatever would make this 0, in this case negative 2, is a multiplicity of, the power here is really 1, so it's a multiplicity of 1. Right here, negative 14 would make that 0. Negative 14 is a multiplicity of 1. And all those things are going to help us kind of trying to figure out what exactly is going on when we see polynomial functions. So looking at this particular polynomial, where we have x minus 3 squared times x plus 1, find the x and y intercepts of f. This part, part number 1, shouldn't really look any different to you than what we've done before with this. So for the x-intercepts, the x-intercepts is whatever we have to put into here, whatever x value has to go in order to get 0 out. Well, if the x minus 3 quantity is equal to 0, we'd get 0 out, or the x plus 1 quantity is 0, we would get 0 out. In this case, x would need to be 3, and in this case, x would need to be negative 1. The x-intercepts are at 3 and negative 1. Keep in mind, if it asks for ordered pairs, you'd have to do 3, 0 in parentheses, or as an ordered pair, negative 1, 0 in parentheses, or as an ordered pair. The x-intercepts, so if I do ordered pairs, we would have 3, 0 and negative 1, 0 as the ordered pairs. The y-intercepts are when it is neither left nor right, so we're putting 0 in. So 0 minus 3 squared times 0 plus 1, we're going to get 9 times 1, or 9. The y-intercept is 9. As an ordered pair, that would be 0, 9 for a y-intercept. Use the x and y-intercepts to determine the intervals where f is above and below the axis. Well, how are we going to do that? From those x and y-intercepts, I know that this graph is touching at negative 1. I know it's touching there. And I also know that it's touching the x-axis at positive 1, 2, 3, touching there. The y-intercept is up here at 9. So we've got this point, and this point where it's for sure touching the graph. What's happening outside of those points? Well, what's happening before -1? So what's happening when we put in values that are less than -1 or before -1? Let's try -2 here once. If I put in -2 into this formula, I'm looking, I'm not even going to try to figure it all out. I look at this term right here. This inside is going to be a negative. A negative squared is a positive. So this is going to be a positive times. Here, this is a negative. Our answer is going to be negative. So I know before this graph hits the -1, it's in the world of negatives. So it's going to be coming from somewhere down here. Then, after it hits 1, after it hits -1, it obviously goes up here, touches there. At some point, it's going to have to come back down and touch here. There's no way it could cross and then come back up, because if it crossed and came back up, we would have more zeros. So I know it's starting from down here, goes through that point, comes up, touches. I know it's going to have to come back down and touch this point. Well, what's it going to do after it touches this point? Is it going to go into the world of negatives or positive? So I'm going to try a point after that was the point 3. So after 3, how about 4? If I put 4 into this equation, 4 minus 3 squared times 4 plus 1. Here, I'm looking at that. I see this is going to be a positive. Squared is a positive. This here, positive. So, positive times positive is positive. After it touches this point, it's going to have to go back up into positive world. And so using those intercepts and also a few other points before and after, I know where this is above 0 in here and below 0 down here. So it's going to be below on the x intervals. So below on the x intervals from -infinity up to, let's see, this was -1. So up to -1. It's going from -infinity up to -1. And then it's above on the interval, on this interval, right in there. So it's above from -1 up to 3. Or, I'll use that or symbol, it's actually on the x-axis at 3. But after 3, from 3 up to infinity, it's above again. So we have this information now. So it's below on this interval, it's above on this interval, and then it's above on this interval. Locate other points on the graph and connect all the points plotted with a smooth continuous curve. So I already kind of located some other points to find out if they were kind of where things were at, whether it was positive or negative. So when I connect those points, we just kind of make smooth continuous curve, just like that. Keep looking at this function here. If r is a 0, so is this the same function? Yeah, it was supposed to be. So we have the same function here. It says if r is a 0 of even multiplicity, that's just saying when we had those zeros, so we had two zeros, our zeros were 3 and -1, those were our two zeros, is a 0 of even multiplicity. The power is even. Here, the power is even, the multiplicity is even. So 3 has even multiplicity. The graph of f touches the x-axis which is what we found. It touches there and then turns around. So it touches and turns around. And so that's what happens when those are even. And the reason that's happening is because no matter whether so here, before it's going to touch, these values in here make this negative, because these values are less than 3, so this is going to make this negative, but that doesn't care. This square is going to still make it positive, and then those values here still make this positive. When it would go across here, when this is even, once it goes across here, now these values we're putting in are bigger, so this is positive, but even though this is positive, this is still an even, so it's still going to stay positive. Nothing is switching with signs there. Whenever we have a square or an even power, it always keeps the signs the same. So that's why it touches, turns around. If r is a 0 of odd multiplicity, our power here is 1. So our power is odd, the graph is going to cross. So odd multiplicity, and the graph crosses there, like that. Turning points are points at which a graph changes direction. Each turning point yields a local maximum and minimum. So once you get farther along, we really care about maximum and minimums, because that tells us things like in something like economics, where we're making the most profit, for example. Or kind of where there's a tipping point or something like that. So turning points are points at which a graph changes direction. In this particular graph, we have 2 of them. There's a turning point here because it changes direction. It was going up, now it's going down. And then there's a turning point there